this. I know, well, okay, yeah, so I've been making mistakes left, right, and center, feels like. That's okay. We'll recover. Let's see here. Let's see here. I'll put it in student. Okay, so I posted the formula sheet for test 1. It's only page 1. So I split it up into pages. So we haven't done any of this. And I think what I'll be doing is cleaning it up as we go, because it's kind of a mess. There's a lot of stuff in here. It's all good stuff and we'll get there eventually. But so I haven't really spent any time on the next few pages there. So if you're printing it, you might have to print it again. I have one copy of the first page that I meant to go and make copies of for you guys, but I was late, so I didn't. So there's one copy on my desk. So I'll bring them on Friday, but they're posted here on Moodle. And of course, you'll get freshies for the test. Let's see here. What else? What else? Oh yeah, this is my mistake. So for this, in this week, I put the test 1 formula sheet, and it was supposed to just be the first page, but it's just the entire formula sheet again. Sorry, I'll re-upload it with just the first page, but now I've told you, so that was my mistake. I posted some chapter 1 and chapter 2 review problems because test 1 is only on chapter 1 and chapter 2. And so they're not for marks, they're just for practice. So if you want them, you got them. And I'll be kind of drawing from assignment questions and these review problems, okay, for the test. I do want to have, so notice how I left Friday kind of open. Usually I like to have a buffer day in case I need to catch up on anything if I run out of time. But also just for going through some assignment problems that maybe were a little bit of a pickle, or from these review problems. So it's kind of, you know, if you're prepared with some problems that you want to work through, then that's great. Otherwise, I'll have a few up my sleeve. Okay. Well, I want those ones, the ones you have up your sleeve. Let's do those. I know, right? How about that? Okay. So if I do say so myself, the Friday videos, I mean, it worked out really well because it was no new material. It was just kind of reworking material that we'd already learned. In terms of 2.4, don't worry too much about kind of what, how to fit the line. We're going to do that in the data science course that you're going to have to take. But it's at the end of the program, I think they put it. It would make more sense if it was just next term. But so you'll see lots of regression in all your other courses. But so this was just a little bite size. Oh, I guess it was, no, 2.4. Okay. Let's see here. Now I'm worried that, okay, it's all good. Get all frazzled. So there was a video about using a TI-83, for example, which I'm not expecting you to do. I think it's useful because there are kind of online calculators that do the same thing. But usually I think you guys will be using Excel for a lot of that stuff. Yeah. And I have heard whispers that you already have fit lines to data. Yeah, no. We have?
We're approaching.
Some people know how to do it.
Yeah.
Yeah.
70%.
All right, that's good enough. I don't have any review, but any questions before how about this? Test number 1 is on Monday. All right. Yes, what is that? October 16th, right? Almost forgetting what year it is. I nearly put 2021. Yikes. I want to go back. No, I don't. Not 2021. Yeah. I guess October wasn't. I don't know. Who knows? Questions will be drawn from assignments and chapter review problems posted. And I just mean those Moodle assignments. Chapter review problems posted. I promise, not out to get you, but that's a lot. Right? All those assignments, making you work for it.
Like we're in school or something.
I know, rude. All those assignments, but they're not for naught, right? You'll get a chance to show off how well you're able to do all those problems on the test. Okay. So, I'm working on a practice test, and I'll post it kind of later today, hopefully. And so then you'll see, but I like to work through the topics as they came. I don't like to do little curveballs of like 2.5 first or anything like that. And so it'll be kind of chronological as we moved through the course. That's nice, right? That's nice. Yeah, I'm not out to get you in any way. You've done the work, so now you just have to show off. All right, and I guess this is a good time to say it, right? If you do poorly on a test, which you're not going to, but if you do, then as long as the final exam is better, then I'll shift one of the weights to the final exam. That goes for if you can't show up for any reason, I don't need to know why, right? That's your lowest grade because you got 0, and then it gets shifted to the final exam. Okay, so I'll do that for one of the 2 tests, and just don't do anything strategic though. It's better to write it and have experienced that test, and then you'll know for the final. Okay. All right. Absolute value functions. Let's grab this here. I can never remember if this is the one that shows you what I'm doing, or does it show you if I do this? Okay, good. I don't like it when it just does things behind your back when I'm copying and pasting stuff. We've seen absolute value functions before. We've seen the graph of the absolute value function, right? The graph is one of those toolkit functions that we need to be able to recognize, right? And just generically, it looks like this. That's supposed to be a proper V. Let's see here. Good enough. So this is the absolute value of x. So we put these vertical bars around it, and it takes a positive number and returns itself, right? Because it's already positive. And it takes a negative value and returns the positive version of itself, right? So here, if you have -2, it returns +2. If you give it +2, it returns 2 again. Right? So it just returns itself. How is it going to do that mathematically? If we have a function and it's the absolute value of x, then it's a piecewise function, right? And so it breaks it up whether x is positive or equal to 0, because 0 is not negative. I'd say it's not really positive either, but anyways, doesn't matter. It's included in the positives. Okay, and so if x is greater than or equal to 0, then it just returns whatever value is inside the brackets x, right? Whereas if x is less than 0, like we saw here, then what does it have to do? It has to do -2, right, in order to turn it positive. So usually when we introduce the absolute value function, we just say, oh, just drop the negative, right? But technically what you're doing is you're negating negative values to turn them into positive values, right? And so here, notice the absolute value negates negative values to make them positive. Yeah. Technically. These are also lines, right? We've just got two lines joining up in, well, here at the origin in this case, but of course it can move around, it can flip around and do all kinds of fun stuff. But here we're just talking about two straight lines. So we know the equation for two straight lines, and we're gonna leverage that fact. Y equals mx plus b, anyone? Let's see here. Or sorry, b plus mx. X. There. Just to warm up and stretch our legs a little bit, our mathematical legs. Let's see here. You have to write an equation for this graph. Knowing that it's an absolute value function is really going to be helpful, right? Recognizing that, hey, I know this shape. This looks like an absolute value function. Let's start there. And then we manipulate that absolute value function. So, right, that's what's one of the toolkit functions to know and recognize. All right. How are we going to do this? First thing we do, right, and maybe I'll just make this just a smidge smaller so I can write here. Step one, I would say, is recognize that it's at its core an absolute value function. All right. Recognize the, can I call it base function? I'll put it in quotes because I don't think that's technically the word, but is the absolute value of x. Okay. So kind of at its core, it's the absolute value of x. Right? So b, so you know it's going to be the absolute value of x. How about step two? What are some things we've noticed? Well, the first thing I've noticed is that it's been flipped upside down. right? That's a good thing to notice. And let me grab it from here. This is when it would have been nice for me to just have the first page. That's okay. Create a new note, import. We've got these transformations. So you'll have these right on the test. So you don't have to memorize them or anything. But what do we want to do? If I want to flip a V that's facing up, if I want to flip it down, then I'm reflecting on the x-axis, right? And so here, let's go back here. All right, the original graph would be something like this. And then I flipped it to turn it upside down. So I flipped it on the x-axis. Flipped on the x-axis, okay, which puts me at negative absolute value of x. Okay. So now we're flipped. So now it looks like this. Now we need to move this thing, but it also looks a little bit wider than the absolute value function. What's the thing about the absolute value function? Hey, I did a pretty good job. Right? The slope of the absolute value function is 1, right? Positive, negative, depending on which side of the axis you're on, right? But regardless, you're going to have a slope of 1, right? And so here, if we look at, and I like to pick kind of nice points that I can tell what's going on here, right? But this has a rise of 1 and a run of 2, as opposed to a rise of 1 and a run of 1. Right? And so now, rise over run, right? For the change in output over the change in input, or whatever you want to call it, right? Now, this slope, 1 over 2 instead of just 1, here we have this 1, negative 1 times the absolute value of x. And so let's see here, step 3, they kind of run into each other. Notice, and you can confirm on the other side as well, but it's also going to be 1/2 for the slope. It's going to be positive, negative, but we can just look at the 1/2. So notice the slope is 1/2 instead of 1. So now we're at negative 1/2 times the absolute value of x. Okay, so that makes this a little bit wider, or just as wide as we wanted it. It's supposed to match, but I'm not drawing very well. Hard part's done, right? Then what do I need to do? I need to move this point. I need to move it up here, right? Which involves a shift to the right, which is the confusing one, right? So I need to shift it to the right by 1, which means from x, and you've got the transformations here. Where are they? I lost them. The formulas. Okay. Sure. Thought I opened them, but okay, so if I want to shift the graph to the right, then I do x minus c, and so go back in here. I don't know where it went. Step 4, shift to the right 1 unit, putting me at -1/2 times the absolute value of x minus 1. All right. If I want to shift to the left or to the right, I manipulate the x. And if I want to shift it up or down, we end on a high note. All right. If I want to shift it up now, what's the color I haven't used? Pink. I never leave pink for last. I want to shift it up.
That's my go-to normally.
It's a good bold color. It's not red. It's not jarring. It's pleasant. I want to go up 2. And so here's step 5. Shift up 2. And hopefully I got this. -1/2 times the absolute value of x minus 1 plus 2. That one behaves as it should. Or at least to me. Emily, is there a way that I can check this work? Because that's crazy. Yes, there is. In fact, well, I already did it. But what's kind of fun is that as you manipulate the graph in Desmos, it's going to make the changes as you go. Okay, so you can always kind of figure out what step where you went wrong. So there's the absolute value button down in the bottom left. And I want the absolute value of x. That's where I'm starting. Okay, that's where we started. And then we said, okay, I'm going to flip it on the x-axis by making a negative. Okay, cool, looks good. And then we said, okay, well, it's actually a little bit wider. And we figured out the slope of the new one was 1/2. And so 1/2 made it wider. Success, looks good. So then inside, we said inside these brackets, we wanted to shift it to the right 1. So -1. Okay, it did. Looks like 2 slots, but it's the axis is weird. And then we wanted to shift it up 2 by +2. Ta-da. And you can check these values. And I'll bring this in. I'm gonna crop this. Oh, try to crop this up. All right. You can use these points to just confirm that that is the same as the graph. This one's going to be hard to confirm. You can kind of convince yourself, right, that it crosses at 1.5. It looks like it does, right? But you can definitely see that it crosses the x-axis at -3 and +5, and the peak is at 1, 2, which all of these are doing. So you did it. Yeah. Drawing on so much knowledge that we've learned so far. Yeah. So in terms of the transformations, that's what I'm expecting you to do. The actual graphing and things is difficult in my opinion. And so that's not something that I want you to be doing by hand. But looking or given a graph like this, I want you to be able to manipulate it and shift things around. Of course, you won't be able to check with Desmos, but do some transformations that way. Okay, nice. Where do I want to go next? Let me see if there's something in here. Nope. How about some examples? We have to solve the absolute value of 2x minus 3 is equal to 8. What are we gonna do? Well, 2x minus 3, it can be 8, or if I take the absolute value of negative 8, it's also going to return 8, right? So what I'm gonna have here is a piecewise function of sorts, right? And so I can have 2x minus 3 is equal to 8, or 2x minus 3 is equal to negative 8, right? The outside can't be negative because the absolute value turns a negative value positive, right? But the inside can be negative. 2x minus 3 can be negative 8, and then the absolute value of negative 8 returns 8. Okay. So I'll make a note of that here. The absolute value of 2x minus 3, if it's equal to negative 8, is equal to the absolute value of negative 8, which is 8. So the inside can be negative, if that makes sense. The inside of the absolute value. Or it can just be 8, right? It can just be the positive value, but either way, the absolute value is going to return 8. So now we have two different, I guess, equations to solve for. And so we're going to get two values of x. So at this point, the math isn't too bad. We've got 2x, we have to add 3 to both sides. So 2x is equal to 8 plus 3, which is 11, right? So x is 11 over 2, or 2x is negative 8 plus 3, putting me at negative 5, right? Someone will stop me if I do my math wrong. Counting on you. Okay. Good. What does this look like? If we were to use Desmos, I can graph this and I can say, okay, ditch that one. It was the absolute value of 2x minus 3. And we want to know, and what I'm going to do, and let me just try something, is equal to 8. No, I don't want that. It does give the answers, but not in the way that I like. And so here, I'm just going to put y is equal to 8. Because what we're solving for is where this absolute value function returns 8, right? It returns 8 at negative 2.5 and 5.5, which, if I have my trusty calculator, I hope. Well, I'm pretty sure, feeling good about this on negative 2.5. How about 11 over 2? Is it 5.5?
Mhm.
Nice. How about x is 5.5 and x is negative 2.5? So graphically, what we're looking at is this. Want to make my screenshot as little as possible. So you can solve it just using Desmos or any sort of graph if you want. But in this case, I think it's easier to just solve it with some algebra. Right? But it's always nice to be able to check your work. Right? All right. Let's see here. How about another? What if we have to solve 4 minus 2 times the absolute value of x minus 1 is equal to 1? Yeah. Because it's just the absolute value function that behaves kind of differently, like it takes a negative value and it returns a positive. What I'm going to do is I'm going to move everything outside the absolute value to the right-hand side. Right? And just get the absolute value on its own. So get the absolute value of x on its own. And in this case, it's the absolute value of x minus 1, but just generically. So I have 4 minus 2 times the absolute value of x minus 1 is equal to 1. I can subtract 4 from both sides. So I get negative 2 times the absolute value of x minus 1 is equal to negative 3. Divide both sides by negative 2. Those negatives are going to cancel. Absolute value of x minus 1 is negative 3 divided by negative 2, which means that the absolute value of x minus 1 is 3 over 2. Okay. Now we're ready. Right, now we can manipulate this absolute value function and we can say, well, I'm actually going to split it up, right? X minus 1 can be the positive version, 3 over 2, or x minus 1 can be negative 3 over 2. And then I get x 3 over 2 plus 1 puts me at 3 plus, I need a common denominator, right? So here, we haven't spent a ton of time on fractions yet, but it's good to remember that you need a common denominator. I like to just multiply by what I want to force the denominator to be, which is a little bit clunkier than finding the lowest common factor and all that stuff, but it always works, and that's the name of the game. So I multiply by 2 over 2. Technically, just multiplying by 1 doesn't change anything. And so then now I have a common denominator. 1 times 2 is 2. So now I get x is 3 plus 2 over 2, which is 5 over 2. Same thing on the other side. I get x is negative 3 over 2 plus 1, which again, times 2 over 2, x is negative 3 plus 2 over 2, putting me at negative 1/2. I can check my work again, and let me just make sure that these are the same. 4 minus 2, x minus, yeah. Sometimes what I have in my pre-baked notes they're not the same, which would be confusing. Okay, 4 minus 2 times the absolute value of x minus 1 and then is equal to 1. Oops, y equals 1. Phew. We did it. Right. Get an output of 1 if x is negative 0.5 and I guess or positive 2.5. How about this one? At first glance, it doesn't look too bad until you kind of take a step back and you realize that, hey, the absolute value of something can't return a negative. That's not what the absolute value function does, right? And so here, I'll even do red. The absolute value can't return a negative. How's that different from the last one? We had a negative at one point, right? We said, okay, if I have 4 minus 2 is equal to 1, I ended up with -3 on this side, but I still had something to bring over and I still ended up at a positive value, right? And so that's one of the things that you want to keep an eye out for, is that the absolute value has to return a positive value. If it doesn't, then what? There are no solutions. There's no value of x that can make a -2, right? So therefore, whoops, therefore, there are no solutions no value of x can turn the absolute value of x minus 4 equal to -2.
That's what you write down, no solution.
Yeah, no solutions. Yeah. There. And then it doesn't hurt to tell me why, right? I can't turn a negative or an absolute value into a negative value. How's that different from when we're doing this, right? X minus 1 is -3/2. All of a sudden, that's fine, right? But why? Because x minus 1 is inside, right? And I'm forcing the inside to be negative. That's allowed. That's a property of the absolute value function, right? But I can't return a negative value, right? And so that's the difference between these two examples. Is here I'm turning the inside negative, which returns a positive value, but we can never return a negative value. What does this look like graphically? Well, I have the absolute value of x minus 4, I think. Nice. Scoot that over. Which I think now that we've kind of worked with transformations, something like the absolute value of x minus 4, we're pretty good at visualizing that, right? Oh, okay, I just take the absolute value, I shift it over 3. And what does that look like? We still have a pretty good understanding of what that looks like, right? I would say the hardest part is when I manipulate the slopes, right? then for me, it becomes a little tricky. But moving things to the left and to the right, maybe even flipping them, I can still visualize moving up and down. I can still visualize that, right? And so we're growing. All right. And I wanted this to be y equal to -2. So now we see that there are no solutions, right? There are no intersections in these graphs, and that's what no solutions looks like. Yeah. And how do I get this all on in one screenshot, one beautiful screenshot? I should probably empty my camera reel at some point. Just so many screenshots. Desmos usually. All right, so here, just highlighting where they are. All right. No intersections. So there are no solutions. So that can happen. That's fine, right? It's a bummer, but the key is to recognize when it's going to happen, and that's when visualizing the graph becomes really useful. All right. Okay. What about if we talk specifically about the intercepts, right? I can have one intercept, right? The y-intercept. I can have two intercepts, or I guess, oh, horizontal intercepts. Sorry. Let me grab this in here so I can draw on it. Horizontal intercepts. Oops. That's easier. Horizontal intercepts are how many times it crosses the x-axis, right? How many times can it be y equals 0, right? So here, remember the y equals 0. So if you have the absolute value function, then you want to solve when does it equal 0, then what are you finding? You're finding the horizontal intercepts. Now, there are cases where, just like we saw in the previous example, right, we don't have any horizontal intercepts. It'll never equal 0. That's fine. That's allowed. It looks like this, right? It'll equal 0 just once when x equals 2 in this case. Right? Or it can equal 0 twice, and that's the maximum, right? Because it doesn't bounce back or anything. It just is a v, and once it's crossed, then that's it, right? It just keeps going down, 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 down. Or it could be facing up, right? It could be facing a v up like this. Either way, it's only going to cross the x-axis at most 2 times. All right. So here's the 1, and here's the 2 horizontal intercepts. All right. And so what we're solving for is, where do these things equal 0? And so let's do an example. We want to find the horizontal intercepts of 5 times the absolute value of x minus 2 minus 3. 5, a multiplier of 5. I can check the transformations. I feel like it tightens it, right? And so x minus 2 shifts me over to the right by 2, and then minus 3 shifts me down by 3. I'm expecting to see 2 intercepts, right? 2 horizontal intercepts. What does this rely on? This relies on us knowing that, okay, I have to set this thing equal to 0 and find where it equals 0. This is really saying find where 5 times the absolute value of x minus 2 minus 3 is equal to 0. We can do that, right? But it does rely on that knowledge, and so that's important. So what we want to do is 5 times the absolute value of x minus 2 minus 3 is equal to 0. Same deal, I want to get x minus 2 on its own, so I have to shake off the 5 and the minus 3. I can do that, right? What do I have to do first? I have to add 3 to both sides, right? And then I have to divide by 5. So I get 5 times the absolute value of x minus 2 is equal to 3. Absolute value of x minus 2 is 3 over 5. Now we're ready. Now I've got this absolute value on its own. And so now I can have x minus 2 equal to 3 over 5, or the inside can be negative, right? X minus 2 is equal to negative 3 over 5. Adding 2 to both sides, I get x is equal to 3 over 5 plus 2. Putting it over 5, multiplying by 5 over 5 to get that common denominator. Right. I get x is 3 plus 10 over 5. 13 over 5. Same thing on the other side. I get x is negative 3 over 5 plus 2. And I'm going to multiply by 5 over 5. And I get ding, 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 ding. Negative 3 plus, I'll write it out, make a match. Negative 3 plus 10 is 7 over 5. Okay. We can check it. We had 5 times the absolute value of x minus 2. Oh, I should be confirming my, let's do that. 5 times the absolute value of x did get tighter, right? Just like I predicted. And then we had minus 2 shifting me over to the right. And then I had minus 3 shifting me down. So I was expecting 2 horizontal intercepts. And hopefully, if I convert my fractions, I get the same thing. (13 over 5) is 2.6. Then this one is hopefully 1.4. 7 over 5. Seems reasonable. Nice. Okay. Nice. So knowing what the graph is sort of gonna look like is gonna help you check your work, right? You won't have Desmos in the test, right? But you've got your brain. You can visualize it. I think it's gonna go up here. And does no solutions make sense, right? What would it look like if there were no solutions? Well, then you would end up with a negative value once you had shook out the absolute value, and then you know that there are no solutions. All right. Okay. I wonder if he has a little. Oh, sure, I'll add this in. Why not? We were just talking about it. I mean, it's pretty obvious, but if you take the absolute value of A and you force it to be B, if B has to be greater than or equal to 0, because otherwise there are no solutions, right? It will have solutions when A is equal to B or A is equal to negative B, right? That's what we've been using up here when we do this split, right? A is equal to B or A is equal to negative B. Right? How are we doing for time? Okay. What if we had to solve something like this? Uh-oh. If you're like me, you don't like inequalities. I don't like them. What are some things we have to remember with inequalities? If I multiply or divide by a negative, it switches the sign, right? That one is confusing. Besides that, it behaves like an equal sign, right? So let's just make some notes here about inequalities. Right, so inequalities behave like equal signs. So usually I just ignore them until the end, unless, and I'll do it in red, unless, oops, we multiply or divide. Dividing is just a special case of multiplication, right? Multiplying by the reciprocal, but unless we multiply or divide by a negative number, in which case the inequality flips. So you always want to keep an eye out for that. But besides that, you're safe to just treat it as an equal sign, right? With that kind of stopper, right? A mental block. Okay. We have to solve this thing. We want to know where an absolute value, it's been squished a little, it's been moved to the right a little, it's been moved up 1, right? And we want to know, where is it greater than 7, right? Just knowing what it looks like is going to help us figure it out, right? And so where is it greater than 7? So not just equal to 7, but 7, 7.1, 7.2, blah, 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 all of them, right? So now we're going to have ranges of X that give outputs greater than 7, right? And so that's what we're going to find. Okay. Let's see here. Do we want to start by, yeah, let's start by graphing this thing. Always with the graph. I know. I'm forcing you to learn to love it. +1. Slowly but surely. Hey, that's what we thought, right? Squished a little, move to the right, moved up. We did it. And then if I draw a line at y equals 7, all right. If I need the output to be greater than 7, what am I looking for? I'm looking for the x values, oops, that give me any value. Why isn't it? Come on. Doesn't want to. There. Right, starting here at 3, 7, and then 3.03, 04, they're all giving me values greater than 7, right? So for any value of x greater than 3, it's going to satisfy that output of being greater than 7. So that's good, right? We can denote that with interval notation, right? And same thing on this side. For any x, come on. For any x, come on, where is it? Trying to get there. Less than -1, right? Here, -1.09, -1.1, these are all yielding values greater than 7. So what we're going to find is we're going to have ranges, right? So intervals where this is true. Okay. So let's see if I can bring this in. I'm gonna, oh, fine, keep the whole thing. I wasn't going to. Okay. So here, we want to find the intervals where this inequality is true, where the inequality is true. What's your first thing that you have to attack here? Well, it's going to be really helpful to figure out where the intersections are, right? We can do that, right? And so, says you, Emily, we can do it. Step 1, find the intersections. Now we're back to where we were working and getting relatively comfortable at 5. Nope, that's not the one I'm looking at. 3. Wow, that would have been confusing, huh? 3 times the absolute value of x minus 1 plus 1 is equal to 7, right? That's how I'm going to find the intersections. That's easier. That's nice. I don't want to be dealing with inequalities. All right, so that's a bonus. This we know how to solve, right? I know I have to get the absolute value, everything inside the absolute value on its own. And so I'm going to start shifting things over. So I get 3 times the absolute value of x minus 1 is equal to 7 minus 1, which is 6. And then the absolute value of x minus 1, 6 divided by 3 puts me at 2. Now that I have the absolute value on my own, well, I guess I did do it on my own. It's not what I meant to say though. X is equal to 2, or x minus 1 is equal to -2. I didn't say the full thing. X minus 1 is equal to 2. Yeah. Okay. Well, this is breezy, huh? X is equal to 3, or x is equal to -1. We already saw that, right? We saw that here, and I should have clicked this one. This is at -1, 7, that point. So we found these points. X is 3 gives me an intersection, and x equal to -1 gives me an intersection. Now, what I'm gonna do is, yes, you can look at the graph, and if you have a good idea of the graph, then go for it. But I also want to introduce something called a sign chart, I think it's called, or sign something, mostly because if you keep going in any sort of math, you'll need it. So it's good to have seen it at least. So what we're gonna do is convince ourselves. So step number 1, convince ourselves that this is a V. It either crosses there either are intersections or there are no solutions, right? Making it easier to solve for. But if we have intersections, which we've already found that there are, right? Then for this entire range, right, or domain rather, or both, I guess, the inequality is satisfied, right? And that's going to be true for any value of x that's less than -1, right? Going to -infinity, right? Going. All the outputs are greater than 7. I think we can convince ourselves of that. Same thing as soon as x is 3 or greater, right? The output is greater than 7, which satisfies the inequality. So what we're going to do is we're going to break up the number line and say, okay, the behavior is the same for these 3 regions, right? And so step number 2 is break up the number line into 3 regions using the intersections. It's more interesting if there are intersections. If there are no intersections, then it's either always true or never true, and you can just plug values in and figure out which one's which, right? What I'm talking about is it can either look like this, right? If this is at y equals 7, well, these are all the outputs are greater than 7, so it's always true. Or if you have something like this, something like this, that's never less or greater than 7, so there are no solutions, right? I don't want to have that there, but I wanted to illustrate what I was saying. But let's focus on this one. So we want to break it up into regions. So now I've got this number line, -infinity to infinity. So we found that at x equals -1, and then at x equals 3, if we didn't have a graph, we know that something happens here, right? It either turns less than 7, right, or greater than 7, or something in between. So what we do is we pick test values, just any value that's in each of these regions, right? So now, and let me just write that as step 3. Step 3, pick test values in each region. 1 will suffice, right? So maybe I'll say pick a test value in each region. Any value, right? The only thing is, and I'm going to copy this here, can draw it on the same thing, but I want to break it up into steps. So picking a test value in this region, I'm going to let x be -2. I like to pick convenient values of x, right? I don't want to think too much. So -2, I always go, if I can, if it allows it, right, I'll pick 0. 0 is between -1 and 3, so that's a go. And then x equals 3 or greater, just any value greater than 3. You could put 1,000 in there. What are you looking for? You're checking to see if the output is greater than 7, right? If it is or it isn't, that determines if the inequality is satisfied. But I'm not going to go crazy. I'll do x equals 5. You can pick any value as long as it's within the regions, right? Picking the intersections is not useful, right? Because we want to know if the inequality is greater than or equal to 7. So now, step 4, evaluate the inequality at the test values. Evaluate the inequality at the test values. So we have, and I just use the original. You can use, well, we don't have the inequality here. I think it's better to just use the original. You don't want to be relying on things that you've arrived at. You always want to be relying on things that were given to you initially. 3 times x minus 1 plus 1 is greater than 7. So if I plug in x is equal to -2, I get 3 times -2 minus 1 absolute value plus 1 is equal to -2 minus 1 puts me at 3. -3 absolute value of -3 is 3. 3 times 3 is 9 plus 1 is 10, which is greater than 7. Right? How about, and that checks out, right? Because we saw from the graph that as long as x is less than -1, we're going to get positive or greater than 7 outputs. What about, and maybe I'll try to shrink this up a little bit so I can fit them all side by side. X is equal to 0, my favorite. 3 times the absolute value of 0 minus 1 plus 1. -1, the absolute value is 1 times 3 is 3 plus 1 is 4, which is less than 7. Just like we saw on the graph. It's more if you don't have the graph, then you need to use sign charts. And finally, my last test point, I think I picked x equals 5. 3 times the absolute value of 5 minus 1 plus 1. 5 minus 1 is 4 times 3 is 12 plus 1 is 13, yeah? Which is also greater than 7. Therefore, the solution is when x is from -infinity, right? Because what we arrived at was that this was a good region and this was a good region and this was a bad region. So now we just translate that into interval notation, usually. So if x is less than -1, so up to and including -1, it's allowed to be -1, it yields 7, right? We found that. And then the union, right, joining these two intervals up, starting at x equals 3 and up to infinity is the rest of the solution. Whew. Not bad. Oh. I'll use the last example for review on Friday. How about that? That'll be good. Any questions? It was all good up until the sign charts usually. And then I lose you. But just remember that it's not up to the test points. Those are arbitrary. It's up to the intersections. All right. Just remember that and you're all good. No. If you have any questions, let me know. Otherwise, I'll see you on Friday. Let's see here.